In this video, we'll apply the Reynolds Transport Theorem to derive the entropy balance for a control volume. So let's start with a refresher of the Reynolds Transport Theorem. So the equation is the derivative with respect to time of an extensive property of our system is equal to the derivative with respect to time of the integral of control volume, our density times our specific property times our differential volume, plus the integral over control surfaces of our density times our specific property times our velocity dotted with the differential area. Okay. So we're not going to get into the Reynolds Transport Theorem. We did that before. We're just going to use the Reynolds Transport Theorem. And in this case, we're going to apply it to entropy. So we're going to make our extensive property entropy and our specific property specific entropy. So we're going to plug that in to our system as such. But then we have this term on the left, differential of entropy of the system with respect to time. We haven't really figured out what that is. So to do that, we're going to go and look at entropy production. So we're going to derive the rate of change of our entropy production. So we started with our entropy production, which we discussed in the previous lesson objective. We say that entropy production is equal to the change in entropy from state 2 to state 1 minus the summation of all the heat transfers from state 1 to state 2 over their boundary temperatures. Well, if we take the rate of time for that, we get that entropy production as a rate is equal to the change of our entropy of our system over time. And then because the temperature is going to be constant in our boundaries, we're going to say the heat transfer rate is going to change. We're going to deal with that instead. So if we rearrange this so that we get that derivative of our entropy of our system with respect to time, well, that's the left side of our Reynolds Transport Theorem. So if we plug this on the right side of this equation into the left side of the previous Reynolds Transport Theorem, well, then we get this new equation with entropy production rate and heat transfers over temperatures on the left with the remainder of our Reynolds Transport Theorem. We're then going to make some assumptions, the first being that this is going to be steady flow, so the first term on the right side goes away. And then we're going to make the assumption of uniform flow. So for uniform flow, we can change those integrals into summations. So we're going to say that it's uniform across these surface areas. And then if you remember that density times area times the velocity, well, that's according to the conservation of mass, that's going to be mass flow rate. So we can then say the entropy balance for a control volume, assuming a steady uniform flow, is going to be our entropy production rate is equal to the summation of the mass flow times specific entropy at the exits minus the summation of the mass flow times specific entropy at the inlets minus the summation of all of the heat transfers going in the process from the inlets to the exits over the boundary temperatures. This is equation 6.14. And so the part on the left, the entropy production rate, this is the entropy created due to irreversibilities. The second term is your rate of entropy that is exiting the control volume with the mass flow rate. And finally, the third term is the rate of entropy changing with heat transfer. This is also your second law of thermodynamics for a steady uniform flow in a control volume. And we can simplify this even further if we make the assumption of 1 in and 1 exit. And then you see that the mass flow just comes out because it's constant for a 1 in 1 exit. This is equation 6.15. And both of these equations are on your reference data card. Now, just to quickly differentiate between entropy and entropy production, because it can be a confusing topic sometimes, we'll start with entropy. Entropy is a property. It does describe a state. It describes that it's the entropy, it's a value at a state. It is not conserved, though. Unlike energy, it can be produced. Okay. The change in entropy is independent of the path of the process. Okay, so we've proven that previously that it's path independent. And there are two ways that you can transfer entropy. You can transfer it via heat transfer, and you can transfer it via the mass flow, which we saw in the entropy balance equation. There were two ways that the entropy could be transferred. Now the entropy reduction, that's part of the balance. That's where we actually have production. It's not a property. It is the entropy that is created during the process. So this is not, entropy is not a conservation principle. We can actually create entropy. It is dependent on the path, so it matters, and you can see that with the heat transfer rates. It matters how much heat transfer it's getting across the boundaries. Now our entropy change, it can either be positive, it could be equal to 0, or it could be less than 0. All those are possible in a real state for entropy change. But there are certain limitations for entropy production. We can use these entropy production rules to classify processes. So we can have some categories of our entropy production. So if your entropy production is greater than 0, that's called an irreversible process. That's what you expect it to be. You expect it to produce some entropy due to irreversibilities. If your entropy reduction is equal to 0, you have a reversible process. So if your entropy reduction is 0, that means no irreversibilities occurred, so it's reversible. If your entropy reduction is less than 0, well, that's an impossible process. So something went wrong there. That's not possible to happen. The lowest you could ever have is equal to 0.